long before the first human crossed an ice-covered landscape, and long after the last dinosaur disappeared, Earth passed through an age that almost nobody talks about. 63 million years of history sit between those two worlds. Not a few centuries, not a forgotten kingdom, 63 million years, and during that time, the planet was rebuilt. At the beginning of this age, Antarctica was covered in forests. Trees grew where ice now stretches to the horizon. The Himalayas did not exist. Neither did the modern pattern of ocean currents that shapes weather across the entire planet. A sea larger than most modern nations nearly vanished, only to return again. Grass spread across the continents and quietly changed the future of life on Earth. And while all of this was happening, the ancestors of every modern mammal were transforming into something new. The lineages that would become horses, whales, elephants, bats, dogs, primates, and eventually humans were all living through this forgotten chapter. Yet most people could not name it. The dinosaurs have an ending everyone remembers. The Ice Age has mammoths, glaciers, and early humans, but between them lies an age that built the modern world and then faded into the background. In this journey, we're exploring the lost 63 million years that transformed Earth from a dinosaur world into the planet we recognize today, and uncovering how the mountains, oceans, climates, and animals around us were shaped during history's most overlooked age. If you're enjoying these long journeys through history, consider subscribing and let me know in the comments where in the world are you listening from tonight. Now, let's step into the forgotten age between dinosaurs and ice. A landscape can survive the loss of its rulers. Forests still grow, rivers still carry sediment toward the sea. Seasons continue their circuits across the continents. 66 million years ago, Earth remained a living planet after the asteroid impact, but the structure that had organized life for more than 165 million years had been removed. Across the continents, ecological positions stood open. The largest plant eaters were gone. The dominant predators had vanished. Entire patterns of feeding, movement, and competition disappeared within a span of time that, in geological terms, was brief. Life persisted, though the arrangement of that life had been profoundly altered. Among the survivors were mammals, creatures that had spent nearly their entire history sharing the world with dinosaurs. Most were small enough to move through dense vegetation unnoticed. Many fed on insects, seeds, fruit, or other modest food sources available near the forest floor. Their bodies reflected that existence. They were adapted to caution, flexibility, and survival in the margins of ecosystems shaped by larger animals. The fossil record preserves the first hints that those limits were beginning to loosen. Within a few 100,000 years, new forms appeared. Teeth became more specialized. Skeletons reveal increasing variation in diet and movement. Some lineages grew larger. Others experimented with lifestyles that had previously been inaccessible. Evolution, operating generation by generation, encountered a world filled with opportunity. Evidence gathered from hundreds of placental mammal fossils, analyzed in research published by University College London in 2015, shows that anatomical diversity expanded at an extraordinary rate during the Paleocene. Across roughly 10 million years following the extinction, mammals diversified faster than at any other period in their evolutionary history. The transformation was not confined to one region or one family. It appeared across multiple branches of the mammalian tree. The setting for this expansion was unlike the modern world. Atmospheric carbon dioxide concentrations were roughly 2 to 3 times higher than present levels. Average global temperatures stood between 10 and 15 degrees Celsius warmer than those of today. Forests stretched far beyond their current limits, extending toward latitudes that now experience snow, ice, and long winters. No permanent ice caps occupied the poles. Antarctica remained free of continental ice. Ocean waters circulated through a greenhouse planet, where warmth reached regions that modern climate systems leave cold. Tropical and subtropical vegetation covered immense areas of land, creating continuous habitats across much of the globe. These conditions formed the opening chapter of the Forgotten Age. The world inherited by the first flourishing mammals was green, warm, and biologically active. Yet the foundations of that world were already beginning to shift. Continents continued their gradual journeys. Mountain ranges had yet to rise. Ocean gateways remained arranged in unfamiliar ways. Processes unfolding beneath the surface were preparing changes that would alter climate, reshape geography, and redirect the course of life itself. For now, the planet carried the marks of loss while also displaying the first signs of renewal. The age of reconstruction had begun, and its starting point was a greenhouse Earth unlike any world that exists today. For a brief interval in deep time, the planet surged in the opposite direction from the path it would eventually follow. The long story of cooling had not yet begun in earnest. Around 56 million years ago, Earth entered a period of warming so rapid that its signature remains visible in rocks scattered across every continent and preserved within sediments far below the sea. Geologists call this event the Paleocene-Eocene thermal maximum, often shortened to the PET-M. Within less than 20,000 years, a span almost instantaneous on geological timescales, global temperatures rose by roughly 5 to 8 degrees Celsius. The source of the warming remains the subject of continuing study. Evidence points toward an immense release of carbon into the atmosphere, measured in the thousands of billions of tons. Volcanic activity associated with the North Atlantic igneous province may have contributed. Methane stored within marine sediments may also have entered the atmosphere. Many researchers suspect several processes operated together. The warming persisted for approximately 150,000 to 200,000 years. During that interval, regions now associated with ice and prolonged winter experienced conditions that seem difficult to reconcile with the modern map. Surface waters of the Arctic Ocean reached temperatures near 23 degrees Celsius. On Ellesmere Island, close to the North Pole, fossils preserve traces of crocodilian relatives and vegetation more commonly associated with warm climates. Their presence records a world operating under very different rules. Far from the sunlight above, changes unfolded across the ocean floor. Deep water, usually buffered against rapid temperature shifts, warmed by more than 5 degrees Celsius. Countless microscopic organisms living within those depths struggled to adapt. Their shells, preserved in sediment layers, still contain chemical evidence of the disruption. It became the largest extinction event affecting deep sea communities during the last 93 million years, written not in bones or footprints, but in subtle variations of ancient chemistry. Life on land followed a different trajectory. Warmer temperatures and elevated carbon dioxide stimulated plant growth across many environments. Flowering plants expanded, insects diversified alongside them, mammals, already exploring newly available ecological opportunities, continued their expansion into unfamiliar forms. Fossils appearing after the Petem include some of the earliest representatives of lineages that would later produce primates, horses, and bats. Evolutionary experimentation accelerated as ecosystems adjusted to altered climatic conditions. The PETIM occupies a distinctive place within modern climate research because it offers one of the closest natural comparisons to the carbon release occurring today through the combustion of fossil fuels. A crucial difference remains in the pace. The ancient release unfolded across thousands of years. Modern emissions are occurring approximately 10 times faster, compressing change into a much narrower window. Eventually, geological processes drew carbon from the atmosphere. Temperatures declined across roughly 150,000 years, and many environmental conditions moved back toward earlier levels. Even so, the planet that emerged carried the imprint of the event. Species distributions had shifted, ecosystems had reorganized, evolutionary pathways had been redirected. Deep within the forgotten age, a burst of heat had altered the course of life, and its effects lingered long after the temperatures eased. There are moments in Earth's history when change pauses long enough for a particular state of the planet to fully express itself. Around 53 to 50 million years ago, during the interval geologists call the early Eocene climatic optimum, the greenhouse world inherited from earlier ages reached its fullest development. Temperatures remained elevated across the globe, creating environmental conditions unlike anything present today. Average surface temperatures are estimated to have stood roughly 10 to 14 degrees Celsius above modern values. Temperature differences between equator and pole were smaller than they are now. Heat reached high latitudes with unusual efficiency, producing a world where climatic zones stretched far beyond their current boundaries. At the southern end of the planet, Antarctica supported ecosystems that would seem misplaced on a modern map. Sediment cores and exposed rock formations contained fossil pollen, preserved wood, and plant remains from forests that covered large portions of the continent. Beech trees belonging to the genus Nothofagus grew there alongside ferns and flowering plants. Growth rings preserved within fossil wood record years of steady development under conditions that included months of seasonal darkness. Life adapted to the rhythm of polar latitude while existing in a climate far warmer than the one associated with Antarctica today. Far to the north, the Arctic Ocean functioned as a partially enclosed basin with limited exchange with surrounding waters. Surface conditions became warm enough to support extensive blooms of azolla, a small freshwater fern now found in tropical and subtropical environments. Layer upon layer of its remains accumulated across broad areas of the Arctic Ocean. Those deposits still form a distinctive band within marine sediments, preserving evidence of one of the most unusual biological events in the Cenozoic. As immense quantities of azolla died and settled into the seabed, carbon that had been circulating through the atmosphere became buried within sediments. The process unfolded over long spans of time, yet its cumulative effect may have contributed to a gradual decline in atmospheric carbon dioxide. A plant no larger than those drifting across modern ponds became part of a planetary process influencing climate itself. Across lower latitudes, the Tethys Sea remained open. Warm waters stretched from regions now occupied by the Mediterranean and Middle East into parts of Asia, linking tropical oceans in a continuous belt. Marine organisms moved through this corridor, and heat flowed with them. The arrangement of continents and seas allowed energy to circulate through pathways that no longer exist. The coastlines of the world also occupied different positions. With little permanent ice available to store water on land, sea levels stood approximately 50 to 100 meters higher than today. Shallow seas extended across areas now occupied by plains, deserts, and mountain foothills. Many landscapes familiar to modern geography had yet to emerge. This interval marked the high point of the Forgotten Ages greenhouse chapter. Conditions fluctuated from place to place, yet the broader trajectory had reached its summit. From here onward, the climate system would begin a gradual descent, measured across millions of years, carrying the planet toward a different state than the one that had flourished under Eocene warmth. Maps often create the impression that continents belong exactly where they are, Their outlines appear fixed, their relationships permanent. During the Forgotten Age, however, one of those continents was still traveling. India spent millions of years crossing the Tethys Sea, moving northward at a pace estimated between 15 and 20 centimeters per year, among the fastest sustained plate motions known from the geological record. Its journey began long before mammals started diversifying across the greenhouse world. Detached from the southern supercontinent Gondwana, India moved as an isolated landmass surrounded by ocean. Geological evidence suggests an unusually rapid passage across thousands of kilometers of open water. Even today, researchers continue examining how such extraordinary speed became possible within the mechanics of plate tectonics. Eventually, movement met resistance. Around 50 to 40 million years ago, the northern edge of India reached Asia. Continental crust behaves differently from oceanic crust. It is lighter, thicker, and difficult to force downward into the mantle. When the two land masses collided, neither could easily sink. Compression became the dominant process. Rock layers that had accumulated across ancient coastlines and seafloors began folding, stacking, and thickening. The process unfolded across spans of time difficult to visualize in human terms. A mountain range was not raised in a moment. Elevation accumulated incrementally as crust continued shortening and uplifting through millions of years of convergence. The Himalayas emerged from this collision. Today they contain 14 peaks exceeding 8,000 meters in elevation, including Mount Everest, the highest point on Earth's surface. Their existence can be traced directly to the continuing interaction between the Indian and Eurasian plates. Each year, India advances slightly farther north, and each year portions of the range continue adjusting in response. A second geographic feature arose alongside the mountains themselves. North of the Himalayas, crust compressed into a broad elevated region known as the Tibetan Plateau, covering an area comparable to Western Europe and averaging more than 4,500 meters above sea level. It represents the thickest concentration of continental crust on the planet. The plateau functions as both a geological structure and a climatic force. Air moving across southern Asia encounters this elevated terrain and cannot pass through it unchanged. Moisture carried from the Indian Ocean rises along the mountain front, cools as it ascends, and condenses into rainfall. This process contributes to the monsoon system that influences agriculture, ecosystems, and water supplies across much of South Asia. On the opposite side of the range, descending air becomes drier, helping shape the arid landscapes of Central Asia. Through these mechanisms, tectonic activity altered far more than topography. Atmospheric circulation patterns shifted, rainfall distribution changed, river systems reorganized. Weather experienced by billions of people today remains linked to crustal movements that began during the Forgotten Age. The collision continues in the present, preserving a direct connection between deep geological time and the modern world. Mountains, plateaus, and climate patterns all emerged from the same source, the gradual convergence of two continents whose meeting reshaped an entire hemisphere and became one of the defining engines of planetary transformation. At the edge of South America, where the continent narrows toward a scattering of islands and storm-driven seas, one of the most consequential geographic changes in recent Earth history unfolded through movement so gradual that no living creature could have perceived it. Rock shifted, seafloor spread, distance accumulated. Across millions of years, a marine gateway widened between South America and Antarctica. The opening that emerged is known today as the Drake Passage. During earlier chapters of the Forgotten Age, that connection either did not exist or remained too shallow to permit unrestricted circulation around Antarctica. Ocean currents, approaching from lower latitudes, could still transport warmth toward the continent. Water carried energy with it, and that energy limited the formation of permanent ice. Geography often acts as climate's unseen framework. Rearrange the continents, deepen a channel, close a seaway, and atmospheric and oceanic systems begin responding. Around 34 million years ago, the Drake Passage reached a configuration that allowed deep water to move continuously around Antarctica. For the first time, a complete ring of ocean circulation became possible. Cold water now flowed eastward around the continent without interruption from land. This circulation pattern prevented large quantities of warmer water from reaching Antarctic shores. Heat that had previously arrived from lower latitudes was diverted elsewhere. The continent became increasingly isolated from the rest of the world's ocean system. Scientists call this circulation the Antarctic Circumpolar Current. By volume, it exceeds every other ocean current on Earth. Approximately 130 million cubic meters of water move through it every second, a flow more than 100 times greater than the combined discharge of all rivers entering the global ocean. Its scale is difficult to visualize. Entire ocean basins participate in its motion. As circulation patterns shifted, Antarctica entered a different climatic regime. Atmospheric carbon dioxide concentrations were also declining during this period, creating conditions increasingly favorable for large-scale glaciation. Together, these changes crossed a threshold. Snowfall accumulated faster than seasonal melting could remove it. Ice expanded, elevation increased. Higher ice surfaces promoted further cooling, strengthening the process. Within roughly 400,000 years, a brief interval in geological terms, the Antarctic ice sheet became established. Once formed, it transformed the continent. Forests and wetlands that had persisted through earlier chapters of the Forgotten Age disappeared beneath expanding ice. Antarctica entered a state it has maintained ever since. Consequences spread far beyond the polar region. As growing ice sheets locked increasing amounts of water onto land, global sea level fell by approximately 50 to 70 meters. Coastlines migrated outward. Continental shelves emerged from shallow seas. Marine corridors narrowed or vanished. Areas formerly separated by water became connected through exposed land. Ocean chemistry and circulation also changed. Colder conditions encouraged the formation of dense water masses that sank toward the deep sea, helping reorganize how heat, oxygen, and nutrients moved through the world's oceans. Regions of marine productivity shifted location. Food webs adjusted to new patterns of upwelling and circulation. The ocean currents familiar today emerged within this transformed framework. The Gulf Stream, the Humboldt Current, and the global conveyor of thermohaline circulation all operate within a planetary system reshaped by the opening of the Drake Passage. A widening channel between two drifting continents altered the climate of an entire world, and its influence continues with every movement of water across the modern sea. A line drawn through a cliff face can sometimes divide two worlds. In parts of Europe, paleontologists studying layers of rock encountered exactly that phenomenon. Fossils collected from sediments below a particular boundary belong to one community of mammals. Fossils recovered from layers above belong to another. The transition appeared so abrupt that it demanded an explanation. Species that had occupied the continent for millions of years seemed to vanish, replaced by unfamiliar newcomers arriving from elsewhere. This event became known as the Grande Coupure, a French phrase meaning the Great Cut. The term was introduced in 1910 by Swiss paleontologist Hans Georg Stellen after he recognized the scale of the transformation preserved within the fossil record. What he observed was not a gradual blending of faunas. It resembled a biological reshuffling occurring across a surprisingly narrow interval of geological time. The mammals living in Europe before this boundary were products of the Eocene greenhouse world. Their ancestry stretched back through warmer climates and ecosystems that had persisted for millions of years. Many belonged to lineages with no living counterparts. Forest-adapted herbivores browsed vegetation across landscapes very different from those that would later emerge. Predators, prey, and plant communities formed ecological networks shaped by conditions that had dominated much of the Forgotten Age. As cooling intensified across the planet, those systems came under increasing pressure. Temperature patterns shifted, habitats contracted, expanded, or fragmented. Geography changed alongside climate. Falling sea levels exposed land that had previously been submerged, creating routes of movement where barriers had once existed. One of the most important changes occurred at the Turgai Strait, a shallow seaway that had long separated Europe from Asia. As sea levels declined, this watery divide diminished and eventually gave way to land connections. Mammals that had evolved across Asian environments gained access to territories that had remained isolated for immense spans of time. The fossil record captures their arrival. Above the Grande Coupure boundary appear animals whose closest relatives originated farther east. They entered ecosystems already undergoing climatic stress and competition intensified. Approximately 50% of endemic European ungulate genera disappeared at or near this transition, representing one of the most substantial turnovers among land mammals during the Cenozoic. The process was not confined to Europe. Across Asia, paleontologists recognize a broadly comparable event known as the Mongolian remodeling. There, too, mammal communities changed rapidly as environmental conditions shifted. Distinct groups declined, others expanded, and ecological structures reorganized. Though regional details differed, both events appear linked to the same planetary cooling trend initiated by transformations unfolding far to the south. That connection remains one of the most striking aspects of the Grande Coupure. A widening ocean passage near Antarctica altered circulation patterns. Those circulation patterns influenced climate. Climate affected sea level. Sea level reshaped geography. Geography opened migration routes. Migration changed ecosystems, thousands of kilometers away from the original source of disturbance. Few events in paleontology illustrate interconnectedness so clearly. No impact crater marks the boundary. No layer of ash records a sudden catastrophe. The agents of change were ocean currents, climate systems, coastlines, and time itself. Together, they produced a replacement of animal communities so extensive that paleontologists can still trace it through a single dividing line preserved in stone where one Europe ends and another begins. Imagine looking down upon the planet during the middle chapters of the Forgotten Age and seeing oceans functioning as walls. Not walls of stone, but barriers just as effective. Water separated continents from one another for millions of years, limiting movement and allowing entire ecosystems to develop in relative isolation. Life continued adapting everywhere, yet each major landmass was writing its own evolutionary story. South America provides one of the clearest examples. For much of the Forgotten Age, it remained detached from North America by hundreds of kilometers of open ocean. No continuous land bridge connected the two continents. Mammals living there evolved without competition from northern groups, producing a collection of forms unlike those found anywhere else on Earth. Predators emerged from lineages unknown outside the continent. Herbivores explored body plans that resembled animals elsewhere, while descending from entirely different ancestors. Some developed long limbs for running across open terrain, others became large browsers. Ecological roles familiar to biology were present, but the actors filling those roles belonged to uniquely South American branches of the evolutionary tree. Africa followed a different path. Connections with Eurasia appeared and disappeared through changing geography and sea levels, creating periods of exchange interrupted by intervals of separation. This partial isolation allowed distinctive groups to persist longer than they might have elsewhere. Evolutionary trajectories remained independent enough for unusual communities to develop, while still receiving occasional arrivals from neighboring continents. Farther east, Australia drifted northward after separating from Antarctica. The continent carried with it a mammalian fauna dominated by marsupials. Without widespread competition from placental mammals, those lineages diversified into ecological positions occupied elsewhere by entirely different groups. Grazers evolved, predators evolved, burrowers, climbers, and omnivores appeared. The underlying reproductive strategy remained distinct, yet the ecological outcomes often resembled patterns seen on distant continents. These parallel developments reveal one of the most important themes in evolutionary biology. Similar environmental challenges frequently produce similar solutions, even when the organisms involved share little recent ancestry. A grassland favors efficient runners. Large herbivores require ways to process vegetation. Predators benefit from speed, strength, or sensory specialization. Natural selection repeatedly discovers workable designs. This process is known as convergent evolution. Across the fossil record of the Forgotten Age, examples appear again and again. South American mammals evolved features resembling horses despite lacking close relationships to true horses. Australian marsupials developed body forms comparable to placental carnivores elsewhere. Separate lineages approached similar outcomes through entirely different evolutionary routes. While continents pursued their individual experiments, geography itself continued changing. The Tethys Sea narrowed as surrounding landmasses shifted position. For hundreds of millions of years, it had served as a major pathway for tropical ocean circulation, distributing heat across equatorial regions. Its gradual closure altered those patterns, influencing climate across large portions of the globe. The significance of these isolated worlds extends beyond the species they produced. They demonstrate that evolution is both creative and constrained. Starting materials may differ dramatically, yet environmental pressures often guide life toward recurring solutions. Different continents, separated by oceans and immense spans of time, repeatedly generated organisms filling comparable ecological roles. Across the Forgotten Age, Earth was not operating as a single interconnected biological system. It functioned as a collection of separate laboratories, each shaped by its own geography, climate, and history. Their stories unfolded independently for millions of years, leaving behind one of the strongest demonstrations that life's pathways can diverge widely while still arriving at strikingly familiar destinations. Few evolutionary transformations are as complete as the one that unfolded along the shores of the ancient Tethys Sea. A mammal that once walked on four legs through coastal environments eventually gave rise to animals capable of crossing entire ocean basins, diving thousands of meters, and communicating across distances measured in hundreds of kilometers. The entire transition occurred within the Forgotten Age. The story begins around 50 million years ago along coastlines that now belong to Pakistan and India. There, among river deltas, lagoons, and shallow marine environments, lived a group of hoofed mammals whose descendants would take an unexpected path. Genetic evidence and fossil discoveries have revealed that whales belong within the broader family of even-toed ungulates, making their closest living relatives creatures such as hippos, deer, pigs, and cattle. One of the earliest known forms in this lineage is Pakicetus. At first glance, it would not be recognized as a whale. It possessed long legs, moved comfortably on land, and resembled a terrestrial predator more than a marine giant. Certain features of its skull and ear region, however, reveal a connection to the cetacean lineage. Fossils suggest an animal spending time near water while retaining many characteristics of a land mammal. The fossil record then preserves a sequence unusually rich in transitional forms. Species such as Ambulocetus combined powerful limbs with increasing aquatic specialization. Later forms spent more time in water and less on land. Hind limbs gradually diminished in importance. Bodies became elongated. Tails strengthened. Nostrils began migrating upward along the skull, beginning the process that would eventually produce the blowhole. Hearing changed as well. Sound travels differently through water than through air, and successful marine hunters required sensory systems capable of functioning in that environment. Structures within the skull were reshaped generation by generation. By around 40 million years ago, the archaeocetes, the early whales of the Eocene, had become fully marine animals. They could no longer return to a terrestrial existence. As the oceans themselves changed during the Oligocene, new opportunities emerged. Cooling waters altered marine ecosystems and redistributed prey. Visibility in many environments became less reliable. Under such conditions, sound offered advantages that eyesight alone could not provide. One branch of whales developed increasingly sophisticated acoustic abilities that would eventually culminate in echolocation. This period also witnessed a major division within the cetacean lineage. Toothed whales and baleen whales followed different evolutionary trajectories, creating the two great groups that dominate modern cetacean diversity. Dolphins, porpoises, sperm whales, and orcas belong to the toothed branch. Blue whales, humpbacks, and right whales belong to the baleen branch. Several remarkable fossils capture this transition in progress. Species such as Aetiocetus, Janjucetus, and Mammalodon possessed combinations of traits that seem contradictory from a modern perspective. Functional teeth coexisted alongside anatomical features associated with the eventual development of baleen feeding systems. Evolution was restructuring entire jaws and feeding strategies, while older traits remained temporarily in place. The oceans of the Forgotten Age were changing in other ways as well. Along temperate coastlines, ancestors of seals, sea lions, and walruses adapted to life between land and sea. These early pinnipeds expanded into ecological niches created by shifting climates and reorganized marine food webs. By the time the boundary between the Oligocene and Miocene approached, whale populations had become abundant enough to support new predators. The earliest known megalodon teeth appear in sediments dating to roughly 23 to 25 million years ago. Oceans that once contained no whales had become seas rich with cetaceans, setting the stage for some of the largest predators and largest animals that Earth would ever produce. A blade of grass appears insignificant when viewed alone. It bends in the wind, grows close to the ground, and rarely attracts attention. During the Forgotten Age, however, this modest plant began one of the most influential transformations in the history of life, reshaping continents, animals, and ecosystems on a planetary scale. Earlier chapters of the Cenozoic belonged largely to forests. Trees dominated many landscapes, stretching across regions that today support open plains and savannas. Grass existed, yet it occupied limited spaces along disturbed ground, river margins, and scattered openings in the canopy. For millions of years, it remained a relatively minor component of terrestrial ecosystems. Climate gradually altered that balance. As temperatures declined and continental interiors became drier, extensive forests retreated from many regions. Open habitats expanded in their place. These changing conditions favored grasses, which possessed characteristics well suited to environments experiencing seasonal drought, periodic fire, and increasing exposure to sunlight. The fossil record begins documenting this shift during the Oligocene. By the Miocene, grasslands covered enormous portions of multiple continents. Areas that had once supported continuous woodland became mosaics of open terrain. New ecological opportunities appeared across landscapes that looked fundamentally different from those of the earlier greenhouse world. Grass brought challenges as well as opportunity. Its tissues contain microscopic silica structures known as phytoliths. These particles function almost like embedded mineral fragments. Animals feeding continuously on grass experienced constant dental abrasion. Teeth adapted for browsing soft leaves wore down rapidly when exposed to a grazing lifestyle. Evolution responded with remarkable consistency. Across unrelated groups of herbivorous mammals, tooth crowns became progressively taller. Fossils preserve this transition in extraordinary detail. Lineages separated by geography and ancestry arrived at similar solutions because they faced the same mechanical problem. Animals capable of maintaining functional teeth survived and reproduced. Others gradually disappeared from expanding grassland ecosystems. Changes extended beyond feeding. Open terrain transformed the relationship between predator and prey. Forest environments provide cover, concealment, and short sight lines. Grasslands operate differently. Distances become greater, visibility increases. Escape often depends on speed, endurance, vigilance, and cooperation rather than hiding among vegetation. Many herbivores evolved longer limbs and more efficient locomotion. Herd behavior became increasingly advantageous, allowing multiple individuals to monitor their surroundings simultaneously. Social organization grew more complex in numerous species as collective awareness improved survival prospects across exposed landscapes. Predators adapted in response. Pursuit became more important. Coordination offered advantages when hunting mobile prey capable of sustained running. Selection favored sharper sensory abilities, greater stamina, and increasingly sophisticated behavioral strategies. A plant growing from the soil was indirectly influencing cognition, locomotion, and social behavior across entire food webs. Digestive systems changed as well. Grass contains large amounts of cellulose and relatively low concentrations of easily accessible nutrients. Herbivores evolved specialized stomachs, fermentation chambers, and microbial partnerships capable of extracting energy from this abundant but demanding food source. Entire anatomical systems were reorganized around a dietary resource that had previously occupied only a marginal ecological role. The landscapes associated with the modern world emerged from these developments. African savannas, North American prairies, Eurasian steppes, and countless other grass dominated regions trace their origins to this expansion. Horses, cattle, sheep, antelope, and many other familiar animals carry adaptations shaped by millions of years spent responding to grassland conditions. Among the many forces that transformed the Forgotten Age, few reached so deeply into the structure of life. Grass altered teeth, limbs, digestion, behavior, and ecosystems simultaneously, leaving a legacy that still defines much of Earth's terrestrial surface today. Maps create the impression of permanence. Coastlines appear fixed, seas seem enduring, and continents look settled into their places. During the closing chapters of the Forgotten Age, however, one of the most familiar bodies of water on Earth underwent a transformation so extreme that it scarcely resembles its modern form. For hundreds of millions of years, a tropical ocean occupied the space between Africa and Eurasia. Earlier eras knew it as the Tethys Sea, a broad marine corridor through which warm water circulated across much of the planet. Its existence influenced climate, ocean currents, and the distribution of life across three continents, yet tectonic motion never ceased. Africa continued its gradual journey northward, and the distance separating the two landmasses narrowed with each passing million years. As mountain belts rose and seaways contracted, the Tethys diminished. By the Miocene, only fragments remained. One of those fragments would become the Mediterranean Sea. Although familiar in outline, it occupied a world still being reshaped by geological forces operating far beyond the span of human experience. Near 5.96 million years ago, a critical threshold was crossed. Tectonic uplift restricted the final marine connection linking the Mediterranean basin to the Atlantic Ocean. Water continued to evaporate beneath the warmth of the regional climate, yet replenishment from the open ocean could no longer keep pace. A process began that would rank among the most extraordinary environmental events of the Cenozoic. Geologists call this interval the Messinian salinity crisis. Rather than remaining a stable sea, the Mediterranean entered repeated cycles of isolation and partial reconnection. Evaporation removed immense quantities of water. Salt accumulated layer upon layer across the basin floor. Modern drilling projects have recovered deposits measuring thousands of meters in thickness, preserving evidence of conditions unlike anything found in the region today. At times, enormous portions of the basin may have stood exposed far below global sea level. Imagine descending from the surrounding uplands into a landscape of salt flats, isolated lakes, steep escarpments, and river valleys extending toward a distant horizon. Rivers that once flowed gently into coastal waters responded dramatically. The Nile cut deeply into the exposed terrain, excavating a canyon whose buried remnants remain detectable beneath younger sediments. Life adapted as conditions shifted. Marine habitats contracted and fragmented. Organisms capable of tolerating changing salinity persisted in scattered refuges, while others vanished from the basin entirely. The Mediterranean became a patchwork of environments, repeatedly reorganized by fluctuations in water level and connectivity. The episode endured for approximately 270,000 years, a brief interval in geological terms, though unimaginably long on human timescales. Then another threshold was reached. Around 5.33 million years ago, Atlantic water once again gained access to the basin through the region now occupied by the Strait of Gibraltar. What followed is known as the Zanclean Flood. Evidence suggests that the refilling may have progressed with astonishing speed compared with the duration of the preceding crisis. Water surged through the breach and descended into the depressed basin. Estimates vary, yet many reconstructions indicate flows dwarfing any river system existing today. Across a comparatively short geological interval, deserts disappeared beneath rising seas. Isolated depressions merged into expanding bodies of water. Shorelines advanced across terrain that had stood exposed for thousands of generations. When equilibrium returned, the Mediterranean resembled the sea familiar to modern geography, though its floor retained the memory of its disappearance. The Forgotten Age was filled with gradual transformations, yet occasionally the movement of continents produced changes that felt almost abrupt. The drying and rebirth of the Mediterranean stands among the clearest reminders that even oceans occupy borrowed time. A tree stump preserved in Antarctic rock carries a message from a world that no longer exists. Its growth rings record years of life spent near the southern pole, seasons of darkness and return, cycles repeated across centuries on a continent now buried beneath ice. Few fossils illustrate the scale of Earth's transformation more clearly than a tree that once grew where glaciers now dominate the horizon. At the opening of the Forgotten Age, Antarctica occupied a very different place within the planetary system. Although positioned near the pole, it remained connected to a climate regime that supported extensive terrestrial ecosystems. Sediment cores, fossil pollen, preserved leaves, and fragments of wood reveal landscapes covered by temperate rainforest. Beech trees of the genus Nothofagus formed part of these communities alongside ferns, flowering plants, fungi, insects, and countless organisms whose traces survive only in fragments. The forests stretched across regions that today experience some of the harshest environmental conditions on Earth. Their existence was possible because the continent had not yet become thermally isolated from lower latitudes. Ocean circulation still transported warmth southward, moderating temperatures and preventing permanent continental ice from taking hold. Life adapted to conditions unfamiliar to most modern forests. For months each year, the sun remained absent. Growth rings preserved in fossil wood indicate periods of reduced activity, followed by renewed expansion when light returned. These trees developed physiological strategies suited to prolonged darkness, maintaining themselves through cycles that persisted generation after generation. Forest ecosystems flourished despite challenges that would seem severe in any present day temperate woodland. Across millions of years, however, the balance supporting those ecosystems began to shift. Changes in ocean circulation altered the movement of heat around the globe. Atmospheric carbon dioxide declined from the elevated levels that had characterized earlier portions of the Forgotten Age. Temperatures trended downward. The continent's connection to warmer waters weakened. Vegetation responded gradually at first. Forest boundaries contracted. Species distributions shifted toward regions where conditions remained favorable. Communities that had occupied broad areas became restricted to smaller refuges. Ecological change unfolded across spans of time, so long that no individual organism could perceive the trajectory. As cooling intensified during the Oligocene, the retreat accelerated. Woodlands gave way to tundra. Plant diversity diminished. Expanding ice occupied terrain previously covered by soil and roots. Areas that had supported complex terrestrial food webs became increasingly inhospitable to large-scale vegetation. By approximately 23 million years ago, the Antarctic ice sheet had become an established feature of the continent. Snow accumulated faster than it melted. Layer settled upon layer. Pressure compressed older deposits into ice. The growing mass reflected sunlight, reinforcing cooling and strengthening the conditions that allowed it to persist. a feedback system emerged, carrying Antarctica further from its forested past. Evidence of that earlier world did not vanish completely. Buried beneath kilometers of ice are sediments containing pollen grains, fragments of leaves, fossil wood, and deposits formed from compressed plant matter. Some of those deposits became coal, preserving the remains of forests that once stood beneath polar skies. They remain locked within a continent transformed beyond recognition. Among the many changes explored throughout the Forgotten Age, few were as complete as this one. A landmass rich with vegetation, insects, and ecological complexity became a realm of ice. The transition altered ocean circulation, influenced global climate, and reshaped the future of life across the planet. Antarctica did not merely cool, it became something entirely different, and it has remained that way ever since. A jaw no larger than a human hand can tell the story of an empire inherited. In rocks laid down shortly after the dinosaurs vanished, paleontologists find the remains of mammals that would have passed unnoticed through the undergrowth of earlier worlds. Small bodies, modest teeth, cautious lifestyles. From such beginnings emerged nearly every large animal familiar today. At the close of the Cretaceous, mammals were survivors, not rulers. The largest among them weighed roughly as much as a medium-sized dog. For more than 165 million years, they had occupied limited ecological roles, while dinosaurs dominated the landscapes of Earth. Then the structure of the world changed. Ecological positions that had been occupied for tens of millions of generations stood open, waiting for new inhabitants. The transformation that followed unfolded with extraordinary speed by evolutionary standards. During the Paleocene, only a few million years after the extinction event, mammal lineages were already experimenting with larger body sizes and new diets. Fossils reveal teeth adapted for crushing, slicing, grinding, and browsing. Limbs diversified as different groups explored forests, river margins, and open terrain. Evolution was not moving toward a predetermined destination. It was responding to opportunity wherever opportunity appeared. Among the early beneficiaries were the condylarths, a collection of archaic hoofed mammals that possessed no direct modern equivalent. They occupied herbivorous roles once held by much larger reptiles and became some of the first mammals to achieve substantial body size. Their descendants did not survive into the present, yet they helped establish pathways that later lineages would follow. As the Eocene unfolded, the mammalian world became increasingly inventive. Tiny ancestors of horses appeared in forest habitats, walking on multiple toes beneath dense vegetation. Primitive proboscideans emerged, carrying the earliest hints of the lineage that would eventually produce elephants. Early primates navigated branches overhead, while the first bats entered the skies through the evolution of powered flight. Along coastal waters, terrestrial mammals began one of the most dramatic transitions known in the fossil record, gradually becoming whales. Each lineage responded to different pressures, yet a common pattern linked them all. Body plans became specialized, sensory systems improved, diets diversified, locomotion evolved to suit increasingly specific environments. Across continents and oceans, mammals expanded into ecological territory that had previously been unavailable. Cooling climates, shifting vegetation, and changing geography continued to shape these experiments. Some groups adapted successfully and radiated outward, others disappeared entirely. The history of mammal evolution during the Forgotten Age is filled with branches that flourished for millions of years before ending without descendants. By the Oligocene and Miocene, Mammalian diversity reached forms that can seem almost improbable. Enormous browsing species moved across landscapes unlike any alive today. Predators evolved body structures that have no modern parallel. Some herbivores carried combinations of traits that appear unfamiliar even to experienced paleontologists. Evolution repeatedly tested solutions that were later abandoned. One striking example was Paraceratherium, a hornless rhinoceros relative whose shoulder approached 5 meters in height and whose mass exceeded that of any land mammal alive today. At the opposite end of the spectrum, small mammals continued diversifying into niches, requiring agility, intelligence, or specialized diets. Size alone was never the goal. Adaptation was. Seen across the full span of 63 million years, the mammal radiation becomes one of the defining achievements of the Forgotten Age. A collection of modest survivors expanded into forests, grasslands, mountains, rivers, coastlines, and open oceans. The world that emerged carried elephants, bats, whales, horses, primates, and countless extinct forms between them. Every modern mammal lineage traces part of its story to that remarkable interval when possibility spread across the planet and evolution answered with abundance. A map can separate more than land. During much of the Forgotten Age, oceans stood between continents for millions of years at a time, turning entire regions into evolutionary workshops operating beyond one another's reach. Animals on different land masses faced similar challenges, inherited different starting materials, and often arrived at solutions that looked astonishingly alike. South America provides one of the clearest examples. For most of the Forgotten Age, it remained detached from North America by broad stretches of ocean. Species that evolved there did so without elephants, horses, camels, bears, or many of the mammalian groups familiar elsewhere. Isolation did not prevent complexity, it encouraged invention. Among the most striking South American creations was Pyrotherium. This massive herbivore carried tusks, possessed a flexible snout, and developed a body form that strongly resembled an elephant. Genetic relationship played no role in that resemblance. Pyrotherium belonged to a completely separate branch of mammalian history. Faced with comparable ecological demands, evolution assembled a similar design from different raw materials. The result looked familiar while emerging from an entirely unrelated ancestry. Other South American mammals followed comparable paths. The Lidopterns, a distinctive group found nowhere else, gradually evolved limbs adapted for efficient running across open terrain. Some later forms developed a single dominant toe that produced a hoof nearly indistinguishable from that of a modern horse. The resemblance became so striking that for decades, paleontologists debated their relationships. Molecular evidence eventually confirmed what anatomy alone had obscured. These animals had arrived at a horse-like form independently, separated from true horses by deep evolutionary distance. Far across the Atlantic, Africa experienced a different kind of isolation. Connections with Eurasia appeared and disappeared as sea levels shifted and tectonic forces altered coastlines. Those intermittent barriers allowed older lineages to survive there long after they had vanished elsewhere. Among them were the hyenodonts, formidable predators that once occupied top carnivore roles across multiple continents. While their relatives disappeared from Europe, Asia, and North America, African hyenodonts continued hunting for millions of additional years. Their persistence reflected geography as much as adaptation. Reduced contact with Eurasian competitors delayed ecological replacement and allowed a fading lineage to endure far beyond its former range. No continent carried isolation further than Australia. After separating from Antarctica and drifting northward, it became home to one of evolution's most distinctive experiments. Marsupials expanded into ecological positions occupied elsewhere by placental mammals. Large herbivores grazed open habitats. Predatory forms stalked prey. Burrowers, climbers, omnivores, and specialists diversified across the continent. What makes this remarkable is that marsupials and placental mammals differ fundamentally in reproduction. Their young develop through different biological pathways, yet natural selection repeatedly guided them toward comparable ecological outcomes. Similar environments encourage similar body plans even when evolutionary histories diverge dramatically. Across all these continents, a recurring pattern emerged. Large browsers evolved, fast runners appeared, apex predators took shape. Ecological roles were filled again and again by unrelated lineages responding to similar pressures. The fossil record preserves these repeated solutions with remarkable consistency. Viewed together, the isolated worlds of the forgotten age reveal that evolution is both inventive and constrained. It explores countless possibilities, yet certain forms return repeatedly when circumstances demand them. Separate continents became separate laboratories, each conducting its own experiment across millions of years. Although the participants differed, many of the conclusions echoed one another across oceans, producing a world richer in diversity than the one that exists today. No coastline, mountain range, or forest marked the boundary of this transformation. It existed everywhere at once, surrounding every continent, filling every valley, crossing every ocean. Throughout the forgotten age, the atmosphere itself formed part of the landscape, shaping life through properties that could not be seen yet influenced every leaf, branch, and animal body on Earth. During the warmest intervals of the Eocene, atmospheric carbon dioxide concentrations are estimated to have ranged between 1,000 and 2,000 parts per million. Modern levels, despite substantial increases during the industrial era, remain far below those values. The difference extended beyond temperature. It affected the basic conditions under which plants gathered energy and converted sunlight into living tissue. Forests flourishing during those greenhouse millions of years grew within an atmosphere unusually rich in carbon. Leaves could acquire the raw material needed for photosynthesis with greater ease. Growth rates increased. Biomass accumulated more rapidly. Ecosystems stored larger quantities of organic matter. Across broad regions of the planet, vegetation achieved densities difficult to sustain under later climatic conditions. Plant communities responded not only to warmth but also to chemistry. Every tree, fern, shrub, and flowering plant existed within a system where atmospheric composition influenced how efficiently energy moved through food webs. More productive vegetation supported larger populations of herbivores, which in turn sustained increasingly complex ecological networks. The structure of entire landscapes was tied to the composition of the air surrounding them. The gradual decline of atmospheric carbon dioxide unfolded across tens of millions of years. No single event caused it. Multiple geological processes operated simultaneously. Fresh rock exposed by mountain building reacted chemically with rainfall and atmospheric gases. Rivers carried dissolved minerals toward the oceans. Marine organisms incorporated carbon into shells and sediments. Biological productivity transferred additional carbon into long-term storage beneath seafloors. Each contribution was modest on human timescales, yet together they steadily altered planetary conditions. As concentrations decreased, plants encountered a changing environment. Strategies that had worked efficiently under earlier atmospheric conditions became less advantageous in certain regions. Competition intensified among lineages capable of extracting carbon more effectively. Evolution responded through experimentation, producing innovations that would eventually reshape entire continents. One of the most significant developments was the spread of the carbon fixation pathway known as C4 photosynthesis. This adaptation allowed grasses to maintain productivity under lower carbon dioxide levels while also performing well in hot, seasonally dry settings. Rather than depending on the conditions that had favored many older plant communities, these grasses thrived as climates became increasingly variable. Their success transformed ecosystems. Grasslands expanded across continental interiors. Savannas spread through regions once dominated by denser vegetation. New opportunities emerged for grazing animals adapted to harvest tough, silica rich plants. Predators, scavengers, and countless smaller organisms adjusted alongside them. A shift in atmospheric chemistry propagated through roots, leaves, teeth, digestive systems, and food chains. Today, see, four grasses contribute roughly 1/4 of global terrestrial primary productivity and dominate many of Earth's largest biomes. Their rise traces back to atmospheric changes that unfolded gradually through the Forgotten Age. Seen across millions of years, the decline of carbon dioxide did far more than cool the planet. It altered the invisible framework within which life operated. By changing the chemistry of growth itself, the atmosphere helped determine which plants prospered, which ecosystems expanded, and which evolutionary pathways became possible. A hillside can sometimes function as a library. Each layer of rock holds a page, each fossil a sentence, and each band of sediment preserves a fragment of a world that no longer exists. Few places reveal this more clearly than the landscape now known as Badlands National Park in South Dakota, where erosion has opened an extraordinary archive from the Forgotten Age. The striking ridges, pinnacles, and gullies visible today belong largely to the White River Formation, a sequence of sedimentary deposits accumulated across roughly 10 million years during the Oligocene. Rivers wandered across broad floodplains. Seasonal floods spread mud and sand over the land. Wind carried dust across open environments. Volcanic eruptions far to the west released ash that drifted through the atmosphere before settling across the region. Layer upon layer gathered gradually, preserving evidence of changing climates, shifting ecosystems, and countless generations of life. Among these deposits, volcanic ash occupies a special place. To an observer standing on the landscape, an ash layer may appear no different from surrounding rock. To paleontologists and geologists, it serves as a timestamp embedded within the Earth itself. Minerals contained within the ash preserve radioactive isotopes whose rates of decay are known with remarkable precision. By measuring those isotopes, researchers can determine the age of a layer and anchor nearby fossils to specific intervals in time. This capability transforms the Badlands from a collection of fossils into a chronological record. Many fossil sites elsewhere preserve organisms without preserving their exact position in history. The White River Formation often provides both. Scientists can connect animal communities to dates measured in millions of years, while narrowing uncertainty to spans measured in tens of thousands of years, a level of resolution that is exceptional for deep time. The rocks also document environmental change unfolding across the Oligocene. Lower portions of the formation preserve evidence of landscapes that retained stronger connections to the warmer conditions inherited from earlier ages. Plant remains, soils, and animal assemblages indicate habitats that supported richer vegetation and more extensive woodland cover. Higher layers tell a different story. Conditions became drier. Open environments expanded. Grasslands and semi-arid habitats increased their influence across the region. That transition can be followed directly through the fossils themselves. Species adapted to one set of conditions gradually decline, while others become more common. The pattern resembles a long ecological conversation recorded in stone, each layer adding another chapter. Climate change is not inferred from a single clue. It emerges from hundreds of interconnected signals preserved together. The archive remains active because the landscape continues changing. Wind, rain, freezing temperatures, and runoff steadily remove sediment from exposed slopes. Measurements indicate that portions of the Badlands erode by roughly 2.5 centimeters each year. Material buried for tens of millions of years can emerge at the surface within a single season. For that reason, the Badlands are not merely a place where fossils were discovered in the past. New specimens continue to appear as the land reveals pieces of its history. Bones, teeth, shells, and traces of vanished ecosystems emerge from rock that has protected them since the Oligocene. Seen in this way, the Badlands function as a genuine passage through time. The same processes that once buried living communities now uncover them, allowing the forgotten age to remain visible in the present landscape. Recognition arrives gradually in the fossil record. A jaw suggests a future lineage. A foot hints at a form not yet realized. A skull carries proportions that seem faintly familiar. Throughout the forgotten age, many of the animals that would eventually dominate modern ecosystems existed only as small, incomplete previews of what was still to come. Among the clearest examples is Mesohippus, an Oligocene relative of the horse. Standing roughly 60 centimeters at the shoulder, it would have looked modest beside the animals that roam grasslands today. Its feet retained 3 functional toes rather than a single hoof, and its body remained suited to environments where open woodland and patchy vegetation still shaped daily life. The elongated face associated with modern horses had begun to emerge, though only as an early draft of a design that would continue changing for millions of years. Its world demanded different solutions from those required later on expanding grasslands. Speed mattered, but not in quite the same way. Feeding strategies remained tied to vegetation, unlike that which would dominate future landscapes. Mesohippus was not a small horse waiting to become a larger one. It was a successful animal, occupying its own place within a particular moment of Earth history. The camel lineage tells a similarly surprising story. Oligocene camels, such as Pobrotherium, bore little resemblance to the desert specialists familiar today. They were comparatively small, closer in size to modern goats than to the large camels of Africa and Asia. Their bodies lacked humps. No evidence suggests the extraordinary water conservation abilities that later became hallmarks of their descendants. They inhabited open woodland environments in North America, a continent that served as the birthplace of the camel family long before camels became associated with deserts on the opposite side of the world. Rhinoceroses also occupied forms that would seem unexpected to modern observers. Some Oligocene species possessed no horns at all. Several were relatively slender animals adapted for movement across broad landscapes. Their proportions resembled large tapirs more than the heavily built rhinoceroses alive today. The immense weight, thick skin, and imposing silhouette associated with modern species had not yet become defining features. Farther south, in what is now Egypt, the Fayum fossil deposits preserve early members of the elephant lineage. These animals remained modest in size compared with later elephants. Their trunks existed only in a preliminary form inferred from skull anatomy. Tusks were present, but limited. Looking at their skeletons, it is possible to glimpse the earliest foundations of a body plan that would eventually produce some of the largest land mammals ever to exist. The ancestors of dogs were equally unassuming. Hesperocyanine canids, appearing in Oligocene North America, were small predators with proportions resembling civets more than wolves. Nothing in their appearance would immediately suggest the extraordinary diversity their descendants would one day achieve. Yet, within those compact bodies existed the lineage that would eventually include foxes, jackals, wolves, coyotes, and the hundreds of domestic dog breeds that now share human homes. What makes these fossils so compelling is not their difference from modern animals, but their position within a continuing story. They reveal familiar forms before familiarity had fully arrived. Evolution had not yet reached the shapes recognized today, though the outlines were beginning to emerge. Across millions of generations, changing climates, shifting landscapes, and new ecological pressures refined those outlines until the modern world gradually came into view. There are mountains today whose highest ridges began as seafloor. Shells, coral fragments, and microscopic marine organisms rest inside rock faces thousands of meters above modern coastlines, carried upward through processes so gradual that entire ecosystems vanished while the stone was still rising. Their presence marks the fading of one of the greatest oceans Earth has ever known. For much of the history of complex life, the tropics were linked by the Tethys Sea. Warm, shallow water stretched across the planet in an immense equatorial corridor, connecting regions that now belong to separate continents. Marine organisms dispersed through it. Ocean currents moved through it. Heat flowed along its length, helping maintain the greenhouse conditions that characterized the earlier portions of the Forgotten Age. The Tethys functioned as more than a geographic feature. Warm water absorbs solar energy near the equator and redistributes it across the globe. The broad tropical seaway allowed that transfer to occur efficiently, softening climatic contrasts between low and high latitudes. Moisture circulated through atmospheric systems connected to those waters, supporting forests that extended far beyond the tropical belts familiar today. Change arrived through continental motion, measured in centimeters per year. Africa continued its northward journey toward Europe. India pressed deeper into Asia. Smaller continental fragments and island arcs became trapped between converging landmasses. Piece by piece, the pathways that once connected the Tethys narrowed. Shallow seas became enclosed basins. Marine corridors fragmented into disconnected regions. As these collisions progressed, the geography of an entire hemisphere was rewritten. The formation of the Alps emerged from the compression between Africa and Europe. Farther east, the continuing uplift associated with the India and Asia collision reshaped circulation patterns across southern Asia. The ocean that had once united tropical waters across thousands of kilometers no longer existed as a continuous system. By the Middle Miocene, roughly 15 million years ago, only remnants remained. The Mediterranean, Black Sea, Caspian Sea, and Persian Gulf occupied portions of a former seaway whose original scale had become difficult to imagine. Each basin preserved a fragment of a much older geography, like scattered pages from a book whose beginning chapters had largely disappeared. Climate responded to these changes. Ocean currents followed new routes. Heat that once moved freely through the equatorial belt encountered barriers that had not existed before. Regional rainfall patterns shifted. Seasonal circulation systems across Africa and Asia adjusted to altered distributions of land, sea, and elevation. The effects unfolded over millions of years, blending with other transformations already underway across the planet. Evidence of the lost ocean remains remarkably abundant. Limestone cliffs exposed throughout southern Europe originated from sediments deposited in tropical marine environments. The Dolomites preserve reefs that formed beneath warm seas long vanished. The Zagros Mountains contain marine fossils carried upward during tectonic compression. High within the Himalayas, rocks still record organisms that once lived beneath sunlit coastal waters. Those fossils offer a striking perspective on the forgotten age. Creatures that spent their entire existence drifting, crawling, or growing in shallow tropical seas eventually became embedded within mountain ranges. Oceans became stone. Sea floors became summits. A body of water that once connected continents survives today as scattered traces across landscapes far removed from any shore, preserving the memory of a world assembled according to a different map. A shoreline seems permanent when measured against a human lifetime. Cliffs hold their position, bays appear fixed, harbors remain where maps place them. Across the forgotten age, however, coastlines wandered back and forth across continents with a persistence that reshaped migration routes, ecosystems, and the geography of life itself. Water was the moving boundary. Whenever the planet warmed, the oceans expanded and polar ice diminished. During cooler intervals, growing ice sheets stored immense quantities of water on land. The balance between those two states determined where the sea ended and dry ground began. Through 63 million years, that balance shifted repeatedly, altering the outline of every continent. Near the height of the Eocene greenhouse world, sea level stood approximately 50 to 100 meters above its present position. Much of the familiar coastal geography of today did not yet exist. Along eastern North America, the ocean reached far inland. Low plains that now support cities, forests, and farmland lay beneath shallow marine waters. Around the Gulf of Mexico, coastlines extended hundreds of kilometers beyond their modern limits. Inland basins hosted warm seas where fish, mollusks, and marine microorganisms drifted through environments that have long since vanished. A traveler moving across that world would have encountered different horizons from those known today. River mouths occupied unfamiliar locations. Coastal wetlands spread across regions now far from any shore. Marine sediments accumulated in places where tractors and highways would one day appear. Cooling gradually altered the balance. As Antarctica acquired a permanent ice sheet during the Oligocene, water that had circulated freely through the oceans became locked within expanding masses of ice. Sea level responded with a substantial decline. Geological evidence indicates a fall of roughly 50 to 70 meters within a comparatively brief interval. The change exposed broad stretches of continental shelf around the world. New landscapes emerged from retreating water. Islands joined larger land masses. Peninsulas lengthened. Former seaways narrowed and, in some regions, disappeared altogether. Ecological boundaries shifted as animals encountered routes that had previously been submerged. One of the most influential examples appeared across the Turgai Strait. For millions of years, this shallow seaway separated Europe from Asia, restricting movement between their mammal faunas. Falling sea level transformed the strait into land. The barrier dissolved. Animals that had evolved independently suddenly shared the same continent, contributing to the sweeping biological turnover already etched into the fossil record of that period. Far to the north, another connection followed a more complicated rhythm. The Bering Land Bridge emerged and vanished multiple times as sea level fluctuated. When exposed, it formed a corridor between Asia and North America. When submerged, populations became isolated once more. Mammals crossed in different directions during different intervals, carrying evolutionary lineages between continents and altering ecosystems on both sides of the northern Pacific. Seen across the full span of the Forgotten Age, continental connections were never fixed features. They behaved more like temporary passages opening and closing in response to climate. Ice determined geography as surely as tectonic forces did. Every major shift in sea level produced a revised map, and each revised map influenced the paths along which life could travel, diversify, and endure. A drop of seawater sinking near Antarctica can begin a journey that lasts for centuries. It may travel across ocean basins, slip along the deepest portions of the sea floor, rise thousands of kilometers away, and eventually return to the surface beneath a different sky. That voyage is part of a planetary circulation system whose modern form emerged during the Forgotten Age. The oceans of the early greenhouse world operated according to a different arrangement. Warm conditions extended across much of the globe, reducing the contrast between tropical and polar waters. The Tethys Sea still carried heat through a broad equatorial corridor, helping distribute warmth across low latitudes. Deep ocean water remained comparatively mild, and the density differences that drive powerful modern circulation were far weaker than they are today. As cooling progressed and Antarctica acquired extensive ice, a new process began shaping the chemistry of the oceans. Around the frozen margins of the southern continent, surface waters became colder, denser, and rich in dissolved oxygen. Those waters sank toward the abyss, spreading outward across the ocean floor. Scientists refer to this mass as Antarctic bottom water, one of the most influential components of modern circulation. Its formation altered environments far from Antarctica itself. Deep marine habitats that had persisted under warmer, less oxygenated conditions encountered a different world. Temperature dropped. Oxygen availability increased. Communities occupying the sea floor changed in response. Fossil records from deep marine sediments reveal turnovers among organisms adapted to older conditions, followed by the spread of species better suited to the colder waters now arriving from the south. The movement of deep water also influenced events occurring far above. Nutrients released through decomposition accumulate in the depths. When circulation patterns bring those nutrients back toward the surface, biological productivity can surge. Regions where this upward movement occurs became some of the richest ecosystems on Earth. Along the western margins of continents, prevailing winds push surface water away from shore. The displaced water must be replaced, drawing colder, nutrient-rich water upward from below. This process, known as upwelling, fuels immense blooms of microscopic plankton. Small fish gather to feed on them. Larger fish follow. Marine mammals and seabirds concentrate in the same productive waters. The fisheries associated with the California Current, the Humboldt Current along western South America, and the Benguela Current off southern Africa all depend upon this mechanism. Their extraordinary biological abundance traces back to circulation patterns established as the oceans reorganized during the Forgotten Age. Every anchovy school, every feeding seabird colony, and every whale gathering in these regions is connected to changes that unfolded millions of years ago. At the broadest scale, these developments became part of the thermohaline circulation, often described as a global conveyor of ocean water. The system depends on contrasts in temperature and salinity that create differences in density. Warm tropical surface water and cold polar deep water participate in a continuous exchange linking the world's oceans into a single interconnected machine. That machine remains active today. It transports heat between hemispheres, influences rainfall patterns, regulates climate, and distributes oxygen through the deep sea. The currents, visible on modern maps, are the living expression of an architecture assembled gradually during 63 million years of planetary change, still carrying water along pathways first established when the world cooled and the southern continent froze. Look across much of Earth today, and the outlines feel familiar. Grasslands stretch beyond the horizon, mountain ranges channel weather systems, herds move across open country, while predators follow established routes through terrain shaped by seasonal rainfall. Many of these scenes trace their origins to the Miocene, the final great chapter of the Forgotten Age, beginning approximately 23 million years ago and ending around 5.3 million years ago. The Miocene occupied a transitional position between older greenhouse worlds and the cooler planet that would eventually emerge. Continents approached increasingly recognizable positions. Ocean circulation operated within patterns largely established by earlier tectonic and climatic transformations. The foundations of many modern ecosystems were already present, though still evolving toward forms familiar today. The age did not begin in relentless cold. During the early and middle Miocene, global temperatures remained several degrees warmer than modern averages. A particularly notable interval, known as the Miocene climatic optimum, unfolded between roughly 17 and 15 million years ago. During this period, forests expanded into regions that would later become more open. Sea levels rose modestly. Biodiversity flourished across many environments as warmth temporarily interrupted the longer cooling trend that had guided the planet for millions of years. Evidence of this interval appears in marine sediments, fossil plant communities, and isotopic records preserved within microscopic shells. Together, they describe a world enjoying a brief climatic reprieve. Tropical and subtropical ecosystems occupied broader territories, and environmental boundaries shifted poleward across multiple continents. The reprieve ended. Around 14 million years ago, a significant climatic transition altered the direction of planetary history once more. Temperatures declined. Antarctic ice expanded substantially. The cooling influenced atmospheric circulation, precipitation patterns, and the availability of moisture across continental interiors. Landscapes already changing during earlier epochs entered a new phase of transformation. Grasslands responded with remarkable success. Areas that had once supported continuous woodland or forest increasingly opened into mosaics of grass, shrubland, and scattered trees. The spread occurred across multiple continents simultaneously, though each region followed its own ecological path. Grazing mammals diversified further. Predators adapted to wider visibility and longer pursuits. Entire food webs reorganized around environments dominated by open ground. Few examples illustrate this transition more clearly than Africa. Across large portions of the continent, expanding grasslands reshaped habitats that had previously supported denser vegetation. The African savanna emerged through this long process, becoming one of the most productive and biologically diverse ecosystems on Earth. Its seasonal rhythms, grazing communities, and predator networks developed within conditions established during the Miocene. Amid these changing landscapes, another lineage occupied a more restricted setting. The earliest anthropoid apes appear within Miocene fossil deposits, inhabiting forests that persisted across parts of Africa, Europe, and Asia. They remained creatures of the trees, adapted to life among branches, fruiting plants, and layered forest canopies. Around them, however, environmental conditions continued to evolve. The importance of the Miocene lies partly in this contrast. Forests still existed, yet grasslands expanded. Warm intervals persisted, yet cooling advanced. Older ecosystems endured, while newer ones assembled around them. By the epoch's conclusion, the planet carried a distinctly modern character. The stage upon which later mammals, including the earliest human relatives, would evolve had largely taken shape, built gradually through millions of years of climatic adjustment and ecological change. A museum gallery can create the impression that the forgotten age has been recovered in remarkable detail. Skeletons stand assembled from skull to tail. Timelines connect species across millions of years. Maps trace migrations, extinctions, and transformations. Yet every fossil haul is built upon a record that is far more incomplete than it first appears. The preservation of life has always been selective. Most organisms vanish without leaving any durable trace. Flesh decays, feathers scatter, leaves rot into soil, bones crack, weather, and disappear. For an animal to enter the fossil record, an unlikely sequence of events must occur. Death must be followed by burial. Sediment must arrive before scavengers, microbes, and environmental processes erase the evidence. Geological conditions must then protect the remains across immense spans of time. Forests present one of the greatest challenges to preservation. The Forgotten Age supported extensive woodland and rainforest ecosystems across large portions of the world, particularly during its earlier phases. Those environments teemed with insects, birds, reptiles, amphibians, and small mammals. Most lived among roots, branches, flowers, and dense vegetation where decomposition operated efficiently. A fallen body on a forest floor often disappeared long before sediment could seal it away. Entire communities may have flourished for millions of years while leaving only the faintest geological fingerprints. The richest fossil localities reveal this bias with striking clarity. The White River Badlands of North America, the Fayum Depression of Egypt, and the sedimentary basins of Mongolia preserve extraordinary collections of bones because burial occurred under favorable conditions. Rivers shifted course. Floodplains accumulated sediment. Volcanic ash settled across landscapes. Dry and semi-arid settings often offered preservation opportunities unavailable in wetter habitats. These sites provide invaluable insight into past worlds, yet they represent particular environments rather than complete portraits of entire continents. A consequence follows naturally from this limitation. Some lineages may never be discovered. Species that inhabited forests, mountain valleys, coastal wetlands, or other poorly preserved habitats could have existed without leaving evidence accessible to modern science. Genera may have appeared, diversified, and vanished without a single surviving fossil. Even broader branches of the evolutionary tree may remain beyond recovery. The information carried by living animals is also largely absent. Bone can reveal age, growth, locomotion, diet, and evolutionary relationships. Teeth preserve chemical clues about food and climate. Occasionally, impressions capture skin texture, feathers, or footprints. Beyond those fragments lies a realm that fossils rarely reach. The coloration of an Eocene mammal, the courtship displays of an Oligocene bird, the vocalizations exchanged within a Miocene primate group all belong to moments that vanished as completely as the sounds themselves. For that reason, gaps in knowledge are not signs of failure. They are measurements of preservation's limits. Paleontology works with what geology allows to survive. Every discovery emerges from a chain of fortunate circumstances involving burial, chemistry, tectonics, erosion, and chance. The Forgotten Age has yielded an astonishing archive, yet surrounding every recovered bone is an immeasurably larger history that left no record at all. A reminder that Earth's past is known through fragments illuminated against a much broader darkness. Look closely at any familiar creature, and the Forgotten Age begins to reveal itself. A dog resting beside a doorway, a horse crossing a pasture, a whale moving through open water, each carries a history written across millions of years. That history does not begin in the recent past. Its roots reach into the long interval when climates shifted, continents rearranged themselves, and ecosystems took forms that still shape the world around us. The connection is preserved with increasing clarity as new fossils emerge from rock layers scattered across the globe. Lineages that once seemed disconnected are now linked by sequences of intermediate forms, each recording a small step within a much larger transformation. The Forgotten Age occupies the center of many of those stories. It was a period when evolutionary pathways that remain active today were established, refined, and set in motion. Consider the dog family. Modern breeds differ so dramatically that they can appear unrelated at first glance. Some weigh more than a human adult, while others can be carried in one hand. Their diversity was created recently through selective breeding, yet the deeper foundation of the lineage reaches back to small canids that lived in Oligocene North America. Hesperocyanines moved through landscapes unlike those of the modern world, carrying anatomical traits that later generations would modify again and again. Every domestic dog remains connected to that distant ancestry through an unbroken chain of descent. The same continuity appears in the history of horses. The single hoof of a modern horse is the latest expression of a lineage that once possessed multiple toes. Mesohippus, living among changing vegetation and increasingly open terrain, occupied a stage far removed from the powerful grazers familiar today. Fossils preserve the gradual reshaping of limbs, teeth, and body proportions as environmental pressures shifted across millions of years. The outline of a modern horse emerged through countless small adjustments accumulated over immense spans of time. Across the oceans, an even more dramatic transformation unfolded. The largest animal ever known, the blue whale, belongs to a lineage whose roots extend to the branching events that occurred as marine ecosystems reorganized during the Oligocene. The separation between toothed whales and baleen whales established evolutionary trajectories that still define life in the sea. Modern cetaceans inhabit oceans, structured by the climatic and oceanographic changes explored throughout this journey. Elephants provide another thread connecting past and present. Fossils from Egypt preserve modest proboscideans whose bodies offered only subtle hints of the giants their descendants would become. Generation followed generation, adaptations accumulated, and the lineage expanded into forms capable of shaping entire ecosystems through their feeding behavior and movement across landscapes. The influence of the Forgotten Age extends beyond animals. Seasonal monsoon systems, grasslands stretching across continents, and ocean currents carrying heat and nutrients all emerged from geological and climatic transformations that unfolded during these millions of years. Those processes continue today, operating as inherited features of the planet. Seen from this perspective, the forgotten age is not separated from the present by distance. Every living species represents its continuation. In a direct biological sense, every breath, every ecosystem, and every lineage alive today exists downstream from the climate shifts, tectonic collisions, evolutionary experiments, and ecological transitions that unfolded across those 63 million years. History often arranges itself in memory around turning points. A mountain peak is easier to remember than the long slope leading toward it. A storm leaves a stronger impression than the season that prepared the sky for its arrival. The forgotten age occupies a different place in the story of Earth. It sits between famous chapters, surrounded by events dramatic enough to capture attention, while its own significance unfolds across a slower rhythm. The age of dinosaurs ended in a catastrophe visible even from the perspective of geology. An asteroid struck, ecosystems collapsed, countless species vanished within a geological instant. The event produced a clear boundary in stone, a dividing line recognizable across continents. Such moments attract memory naturally. They possess a beginning, a climax, and an ending. The Ice Age carries a different advantage. Its final chapters overlap with the story of our own species. Human beings walked across landscapes shaped by advancing glaciers. They encountered mammoths, giant deer, and saber-toothed predators. They left paintings, tools, campsites, and traces of daily life. Through those remnants, the Ice Age feels personal. It reaches directly into human experience. Between those familiar landmarks stretches the forgotten age, lacking both catastrophe and personal witness. Its transitions occurred gradually. Temperatures shifted across millions of years. Mountain ranges rose a little higher with each passing age. Ocean currents altered course. Forests withdrew. Grasslands expanded. Species changed generation after generation. No single moment announced that the world had become different. Yet the importance of an event is not measured by how dramatic it appears. The asteroid that ended the reign of the dinosaurs removed dominant forms of life from the stage. The forgotten age filled the empty spaces that remained. During those millions of years, the climate system acquired many of the characteristics it still possesses. Modern ocean circulation emerged. Antarctica transformed into an ice-covered continent. Grasslands spread across continental interiors. Mammals diversified into forms that would eventually become familiar inhabitants of the present world. The contrast reveals something about human cognition itself. Memory favors sharp edges. Beginnings and endings provide convenient anchors for storytelling. A single disaster can be summarized in a sentence. A gradual transformation, extending across tens of millions of years, resists compression. It lacks a date that can be memorized or a scene that can be imagined instantly. Geology operates according to different priorities. Continents do not require dramatic moments to reshape the world. Rivers carve valleys grain by grain. Ice sheets advance meter by meter. Evolution proceeds through populations, generations, and accumulated changes too small to notice in isolation. When viewed across sufficient time, those incremental processes become forces capable of redesigning the planet. For that reason, the Forgotten Age offers a perspective that extends beyond paleontology. It demonstrates that the most influential chapters in Earth's history are often the least theatrical. The landscapes, climates, ecosystems, and animal lineages that define the modern world emerged through persistent change rather than spectacle. Most of Earth's story unfolds in these extended intervals, where consequence accumulates without fanfare, and where the shape of the future is assembled piece by piece long before anyone could recognize what is taking form. A clock can measure a second, A calendar can measure a year. Human experience can stretch across decades. Beyond that, imagination begins to struggle. Deep time occupies a scale so immense that ordinary intuition loses its footing, and the forgotten age stands as one of the clearest examples of that challenge. 63 million years can be written on a page with ease. Understanding its true magnitude is something else entirely. One useful comparison is to compress the whole interval into a single calendar year. In that imagined year, the opening of the Paleocene arrives on the first day of January. The asteroid impact that ended the age of dinosaurs belongs to the final moments of the previous year, separated by little more than a midnight boundary. The Ice Age does not appear until the final evening of December 31st, arriving only minutes before the year ends. Human history occupies an even smaller fraction. Agriculture, cities, empires, writing, navigation, industry, science, and every recorded event known to civilization would be confined to the tiniest sliver at the very end of that final day. The span separating the earliest farmers from the present would be almost invisible against the backdrop of the forgotten age. The organisms living at the beginning and end of those 63 million years would have inhabited worlds profoundly different from one another. Early Paleocene ecosystems still carried echoes of the extinction that had recently reshaped life on Earth. By the close of the age, grasslands stretched across continents, modern mammal groups had diversified, ocean circulation resembled its present form, and Antarctica stood covered in ice. These transformations unfolded gradually, accumulating through countless generations and environmental shifts. Geology provides another perspective on duration. When the Forgotten Age began, the collision between India and Asia was still in its earlier stages. Landmasses moved together year after year, raising mountains through pressure applied with extraordinary patience. The Himalayas visible today are products of that continuing process. Their growth did not cease when the Forgotten Age ended. The same tectonic forces remain active now, carrying forward a story that extends across tens of millions of years. A similar continuity exists at the southern end of the world. The Antarctic ice sheet established during the Forgotten Age has persisted for roughly 34 million years. Snow accumulated upon older snow, ice compressed into denser layers. Entire masses of frozen water flowed outward under their own weight, while fresh snowfall renewed the surface above. Through spans beyond ordinary comprehension, the continent transformed into a repository of climatic history, preserved layer upon layer. Deep time offers a perspective that reaches beyond geology or paleontology. It reveals that Earth is not a finished landscape suspended in permanence. Coastlines shift, mountains rise and erode, oceans reorganize themselves. Ecosystems appear, expand, and give way to others. Every familiar feature exists within a longer narrative of change. The Forgotten Age occupies a special place within that narrative. It was the most recent great interval in which the foundations of the modern world were assembled. Seen against the scale of deep time, the present becomes part of a continuum rather than a destination, another moment within a planet that has never stopped transforming. Many of the legacies left by the Forgotten Age can be traced across maps, mountain ranges, coastlines, and ice-covered continents. Others leave no obvious mark on the horizon. They operate through currents, chemistry, sediments, and biological networks, shaping daily life without announcing their presence. Their influence is continuous, woven into the functioning of the modern planet. Far below the reach of sunlight, one of those systems continues its work. During the cooling transformations of the Oligocene, Antarctica became the source of dense bottom water that sank through the Southern Ocean and spread across the deepest parts of the globe. That movement still persists today. Cold water travels along the ocean floor, carrying dissolved oxygen into regions that would otherwise become stagnant. Deep sea organisms, living thousands of meters below the surface, depend on this circulation. Creatures that never encounter daylight exist within habitats sustained by a process established tens of millions of years ago. The consequences extend beyond biology. Deep currents influence how nutrients are stored, transported, and eventually returned toward surface waters. Every exchange forms part of a planetary circulation system, linking polar seas with equatorial oceans. The arrangement feels permanent from a human perspective, yet it emerged from geological events that unfolded during the Forgotten Age. A similar inheritance can be found in stone. As the Himalayas rose through the continuing collision of India and Asia, fresh rock surfaces were exposed to rain, rivers, frost, and chemical alteration. Minerals weathered and broke apart. Certain reactions consumed atmospheric carbon dioxide and carried the resulting products toward the oceans. This process remains active across the mountain belt today. Year after year, erosion reshapes slopes while participating in one of Earth's longest-running climate regulation mechanisms. The effect is measured on timescales far beyond individual lives. No observer can watch a mountain range remove meaningful amounts of carbon dioxide during a single lifetime. Across millions of years, however, the cumulative influence becomes immense. The relationship between uplift, weathering, and atmospheric chemistry forms part of the hidden framework supporting long-term climate stability. Beneath grasslands, forests, and agricultural regions lies another inheritance. Modern soils are products of prolonged interaction between climate, vegetation, water, microbes, and parent rock. During the later phases of the Forgotten Age, expanding grasslands altered erosion patterns and organic matter accumulation across enormous areas. Rivers redistributed sediments, winds transported dust between regions. Layer upon layer accumulated until landscapes acquired the foundations that support many present-day ecosystems. Agriculture depends upon this history. Fertile plains did not appear spontaneously. Their properties reflect countless cycles of deposition, weathering, and biological activity extending deep into geological time. Harvests grown today are connected to environmental processes that began long before humanity emerged. Across the oceans, patterns of abundance reveal another unseen architecture. Regions supporting dense fisheries often coincide with areas where deep, nutrient-rich water rises toward the surface. Microscopic plankton flourish there, supporting larger organisms through successive levels of the food web. The locations of many of these productive zones correspond closely to circulation patterns established as oceans reorganized during the Forgotten Age. These systems receive little attention because they rarely announce themselves dramatically, yet they regulate oxygen, climate, nutrients, soils, and biological productivity across the planet. The Forgotten Age built more than landscapes. It assembled mechanisms that continue operating every day, sustaining the world from foundations that remain largely invisible. A traveler arriving on Earth during the Pliocene might have felt an unfamiliar sense of recognition. Much of the world assembled during the Forgotten Age had settled into forms that echoed the landscapes of the present. The transformation was not complete, yet the outlines of the modern planet had become increasingly clear. Across the globe, climates remained somewhat warmer than those experienced today. Average temperatures stood roughly 2 to 3 degrees Celsius higher, preserving conditions that supported forests farther poleward than modern distributions allow. Even so, the direction of change had become unmistakable. Cooling continued its patient advance. Antarctica remained locked beneath a continental ice sheet, and signs of seasonal ice were beginning to appear in the Arctic. The climatic machinery, constructed over tens of millions of years, was steadily guiding the planet toward a colder future. The geography of the Earth had also approached familiar arrangements. Continents occupied positions close to those shown on modern maps. Mountain systems, forged through long tectonic collisions, dominated regional weather patterns. The Himalayas towered across Asia, influencing winds and rainfall across an enormous area. Grasslands stretched across Africa, Eurasia, and the Americas, occupying territory once held by forests during warmer chapters of the Forgotten Age. Ocean circulation, reshaped through earlier tectonic and climatic events, operated in a form recognizable to modern oceanographers. Currents carried heat between hemispheres, distributed nutrients through the seas, and influenced weather far from their points of origin. The invisible systems discussed earlier were fully established, linking atmosphere, ocean, and land into a tightly connected whole. Animal communities reflected the same growing familiarity. Horses now carried their weight on a single hoof. Elephant relatives had achieved body sizes approaching those of living species. Members of the cat and dog families occupied predator roles across multiple continents. In Africa, early representatives of the genus Homo appeared within environments shaped by expanding grasslands and shifting climatic boundaries. Their presence remained modest within the wider story of life, yet they formed part of a lineage whose future significance would eventually become extraordinary. Despite these recognizable features, the Pliocene was still an age of motion. One of its most important developments occurred in Central America, where geological forces completed the emergence of the Isthmus of Panama. Around 3 million years ago, the connection between North and South America became continuous land. Two continents that had spent most of the Forgotten Age evolving separately were suddenly joined. The consequences unfolded across thousands of generations. Mammals from the north traveled southward, while South American species expanded into new territory beyond their ancestral homeland. Bears, cats, and canine predators entered ecosystems that had developed without them. Ground sloths, armadillo relatives, and large rodents moved north. Ecological communities, reorganized as migration, competition, and adaptation, reshaped entire food webs. Among the most striking participants were the terror birds, descendants of long-established South American predators. For millions of years, they had occupied dominant hunting roles. The arrival of placental carnivores introduced competitors unlike any they had previously encountered. Many of those bird lineages gradually disappeared as ecological pressures shifted around them. Seen from the perspective of deep time, the ice age that followed was not an abrupt new beginning. It emerged from trends already in motion. The cooling pathway established when Antarctica froze millions of years earlier continued step by step, carrying the planet toward the glacial world that would eventually become the stage for human history. A fossil can reveal the shape of a tooth, the thickness of a bone, or the age of a buried landscape. It cannot preserve a breeze moving through leaves, the scent released after rainfall, or the character of a distant call carried across open ground. Even so, the evidence left behind allows certain features of the Forgotten Age to emerge with surprising clarity. During the early Eocene, the atmosphere contained far more carbon dioxide than it does today. Plants responded with abundant growth, creating forests of unusual density across regions that now support very different ecosystems. Sunlight entering these forests would have passed through multiple layers of vegetation before reaching the ground. Leaves filtered and scattered illumination into shifting patterns. Humidity remained high. Fallen wood, fungi, flowering plants, and damp soil contributed to a chemical richness that modern tropical rainforests only partially resemble. Every indication points toward environments saturated with biological activity. Sound would have carried through those forests as well, though not in a form familiar to modern ears. Many groups common today had not yet achieved their present diversity. Songbirds existed in early forms, yet the communities shaping modern forest acoustics were still developing. Mammalian ecosystems were equally different. The calls, movements, and interactions of Eocene animals belong to combinations of species that no longer share the planet. Their voices vanished long before the first human ancestors appeared. Far later, as climates cooled and landscapes opened, the sensory character of entire continents changed. The Oligocene plains of North America stretched across broad horizons where woodland and grassland mixed unevenly. Wind moved through scattered vegetation and carried dust from exposed soils. Seasonal rivers crossed the terrain, drawing animals toward dependable water sources. Fossil evidence reveals communities adapting to increasing openness, and those changes imply a landscape where distance became more visible and movement across open country more important. Another shift emerged in Miocene Africa. Grasslands expanded across large areas while forests retreated into fragmented regions. The overall scene might appear recognizable from afar. Herds crossed open spaces. Predators followed. Trees stood in scattered clusters. A closer look would quickly dissolve the familiarity. Hooves, limbs, skulls, and teeth often belonged to lineages occupying evolutionary stages that no longer exist. Many species resembled modern forms only in outline, carrying anatomical combinations that later disappeared from the record. Beyond the continents, another environment was undergoing its own transformation. Cold Antarctic bottom water flowed across the deep ocean floor, bringing oxygen into regions previously dominated by different chemical conditions. Life adapted accordingly. Organisms inhabiting those depths became specialists within an expanding ecological system that still operates today. No sunlight reached those communities. Their existence depended on circulation patterns established through planetary change rather than daily weather or seasonal cycles. Looking across the forgotten age through this lens, one impression gradually becomes stronger than novelty. The forests, plains, coastlines, and oceans were distinct from those of the modern world, yet many carried the foundations of systems still active today. Their climates shaped later climates. Their ecosystems gave rise to later ecosystems. Their geological processes continue their work. The forgotten age feels distant when measured in millions of years. Through the traces it left behind, it also feels unexpectedly close, present within the structure of the world that surrounds us now. There is no precise boundary in nature where one world ends and another begins. Geological time is often divided into chapters for convenience, yet the processes shaping the planet rarely pause to acknowledge those divisions. The forgotten age faded into the ages that followed through continuity, carrying forward forces already in motion. The cooling trend that defined so much of its history did not stop when the Pliocene gave way to the Quaternary. Temperatures continued their gradual descent. Ice expanded and retreated in rhythmic cycles driven by variations in Earth's orbit and orientation. The Ice Age emerged from conditions assembled across tens of millions of years, drawing upon atmospheric, tectonic, and oceanic systems inherited from the Forgotten Age. In that sense, the glacial world belonged to the same unfolding narrative. Even now, the collision between India and Asia continues. The process began around 50 million years ago when a drifting continent met the southern margin of Eurasia. Compression folded and uplifted rock into mountain ranges of extraordinary scale. That force has never fully ceased. Modern measurements show India still moving northward, still transferring energy into the crust. Rivers carve through rising terrain, while new rock surfaces emerge to face wind, frost, and rain. The Himalayas visible today remain part of an unfinished construction project. Far to the south, Antarctica preserves another thread connecting the present to the distant past. Ice first became firmly established there during the Forgotten Age, transforming global climate and ocean circulation. The ice sheet remains in place, covering most of the continent beneath kilometers of frozen accumulation. Around its margins, cold, dense water forms and sinks into the deep ocean, feeding circulation patterns that extend across the planet. Every journey made by those currents continues a process initiated millions of years before human beings existed. Across continents, grasslands remain among the dominant terrestrial ecosystems on Earth. Their spread during the Oligocene and Miocene reshaped animal evolution, altered carbon storage, and transformed landscapes. Modern grazers still consume grasses strengthened by silica-rich tissues. Teeth still wear down under the same abrasive particles that influenced evolutionary pathways long ago. The ecological dialogue between grasses and herbivores persists with remarkable continuity. The oceans carry similar echoes. Whale lineages that diversified during the Oligocene continue to navigate marine environments structured by circulation systems established during that same era. Toothed whales employ echolocation descended from adaptations refined over millions of years. Baleen whales migrate through waters whose temperature patterns and nutrient distributions remain linked to tectonic and climatic changes rooted in the Forgotten Age. Humanity occupies this continuity as well. The earliest members of our broader primate lineage evolved within environments shaped by expanding grasslands and changing forests. Climatic shifts altered habitats, migration routes, food availability, and selective pressures across Africa. Those transformations influenced countless generations before the appearance of our own species. Every human life carries biological traces of adaptations forged within that long environmental history. Seen through the lens of deep time, the Forgotten Age does not appear as a vanished world, sealed away in stone. Its systems remain active. Mountains continue rising. Ice continues forming. Currents continue circulating. Ecosystems continue responding to patterns established long ago. The age survives not as memory, but as process. Its work continues beneath every landscape, within every ocean basin, and through every living lineage that inherited the world it created. A footprint pressed into wet ground lasts only moments before weather begins its work. Mountains endure longer, oceans longer still. Across the span we have traveled, one truth emerges with increasing clarity. Duration changes perspective. Things that appear permanent from a human viewpoint become temporary when measured against the age of the planet. The Forgotten Age was never lost to Earth itself. Rocks remember it. Rivers flowing from mountain ranges remember it. Ocean currents crossing entire hemispheres remember it. Living organisms remember it through anatomy, behavior, and inheritance. The disappearance exists only in human awareness, shaped by the limits of memory and the brevity of individual lives. Every consequence remains present. The height of a grazing animal's teeth reflects landscapes assembled millions of years ago. The route, followed by seasonal rains, traces the influence of mountain building that began long before humanity appeared. Whale migrations unfold through oceans organized by circulation systems established during climatic transitions of the Forgotten Age. Even the composition of soils supporting forests, farms, and grasslands carries signals inherited from processes that unfolded across immense spans of time. Earth does not store history in a separate archive. History becomes structure, it becomes geography, it becomes climate. The distinction between past and present begins to blur when viewed through that lens. Events often imagined as finished continue expressing themselves through the systems they created. Seen from within an ordinary day, the world can appear fixed. Roads remain where they were yesterday. Hills seem unchanged. Seasons arrive in familiar order. Deep time reveals another picture. Continents continue their journeys. Ice advances and retreats. Species adapt. Coastlines migrate. Change persists even when it unfolds too gradually for direct observation. Such a perspective does not diminish human experience. It places it within a broader setting. The concerns that occupy a lifetime remain real and meaningful, yet they unfold inside a planet shaped by forces operating across millions of years. Every generation inherits conditions created by countless generations before it, both human and non-human. The Forgotten Age offers an opportunity to notice continuity where we often expect separation. The mountains still rise. Ocean water still circulates between surface and abyss. Grass continues spreading through landscapes favorable to its growth. Evolution remains active, shaping organisms through the accumulation of small changes. The story never paused. It merely moved beyond the limits of immediate perception. Perhaps that is the most enduring lesson carried forward from these 63 million years. Transformation rarely announces itself with a single dramatic moment. More often, it arrives through persistence, through processes repeated across spans so long that beginnings and endings become difficult to identify. Following catastrophe, Earth rebuilt itself without intention and without haste. Forests expanded and retreated, oceans reorganized, mammals diversified, ice gathered on a southern continent. The foundations of the modern world emerged piece by piece until they became the world we know. And so the Forgotten Age remains present, not as a distant chapter sealed away behind us, but as a living inheritance. It shaped the land beneath our feet, the air moving across continents, the water circling the globe, and the lineage through which each of us arrived here. That is enough to rest with.